Well, good morning, everyone. Welcome to your online school day. I want to start out today by going over a couple of corrections and just observations from the homework that you turned in last week. So the first one is if you'll pause this recording for a second and get out your assignment from last Wednesday, I want to make a couple of points here. And I think I maybe responded to some of you individually by email, but I just want to make sure that I point these out to everyone so that we get the mistakes corrected before we get into some of the uglier kinds of equations that we'll be working with over the next week or two. So the first one I want you to look at is number 38 from Wednesday's homework. In that one you had to solve the equation 2 equals the quantity 1 plus r to the 6th power. And you want to make sure that you start out with that by taking the 6th root of both sides. You want to get rid of that 6 that's in the exponent. Some of you wanted to try sort of a newfangled FOIL method for that. That's going to cause you problems. So you want to make sure, again, that you start out by taking the 6th root of both sides. To do that, you'll raise both sides to the 1/6 power. Remember, we talked about that last week in class, that if you had, for example, the square root of something, that's the same as raising that something to the 1/2 power. In this case, if we want to take the 6th root, that's the same as raising that to the 1/6 power. So on your calculator, if you take 2 to the 1/6 power and then subtract 1, you'll solve for r correctly. And number 38, that should have given you 12.25% for that one. Next one I want you to look at is number 42, either 41 or 42, part B. Those were both similar to one another. In each case, you had an equation where you had a variable in the exponent, and you're working with a base of e. And several of you, I noticed, when you took the log base e of both sides. And while that's technically correct, you are taking the log base e. In mathematics, generally, we understand that the log base e is called the natural log. That's the ln that you see on your calculator. And so you want to make sure, so that you don't head off to college and embarrass yourselves, that you don't take the log base e, or at least you don't write it that way. You write it as the natural log, ln, of both sides. So that's kind of a picky point, but again, that's how things are done, and I want to make sure that, again, you don't embarrass yourself when you're in college, and we don't want you to be the one that the university math department professors are standing around saying, hey, guess what this kid did? Don't be that person. All right, so the final correction from last week is on the credit card assignment that you did on Friday. And some of you, actually most of you, had difficulty with calculating the total amount of interest paid. Now, I put the suggestion, the method for how to do that on Edmodo, but I think you had other ideas, so we'll just say it that way. So all I wanted you to do to calculate this interest, and again, if you'll pause this recording, get out that credit card assignment so you can see what I'm talking about. All I wanted you to do to calculate the interest is to take the total amount that you've paid, which is the amount that you're paying each month times the number of months that you made payments, and then subtract from that your original balance. So that's going to take the total amount of money you paid minus the original amount that you borrowed, basically, or that you charged. And then you subtract when you take that difference, you find the amount of interest. The only thing you need to remember is that the last payment that you make might be a partial payment. Let's say that at the end of, maybe you're paying this off over a period of 24 months, and at the end of 23 months you owe $20, but your monthly payment's $100. Well, you're going to overestimate your total payoff by $80 in that case. But this still gives you an approximate idea of how much interest you're paying. Some of you use the simple interest formula that we talked about last week in class. That's going to cause a problem here because it assumes that you just have the same balance each month. And if you're making payments toward that balance, then you don't have the same balance each month. Your balance is going down each month, and so your interest is being recalculated based on the new balance. And that's kind of a new concept. All of the formulas that we dealt with last week, when we were talking about simple interest, when we were talking about compound interest, those formulas all assume that you had a fixed lump sum amount that you were either investing or borrowing. And in the real world, that's generally not the case. You're making payments. You're either making payments to yourself by adding to some kind of a savings account or an annuity or an investment fund, or you're making payments to the bank and lowering the amount that you owe each month, let's say on a mortgage payment or a student loan payment or a car payment. And so we're moving towards that kind of thinking today when we talk about something called an annuity. This material is in section 6.3 of your textbook. I'm going to take a few minutes to go through the development of the formula for an annuity, and then you'll have an opportunity to use that formula today to go through some practice exercises. So let's go ahead and get started. You've been looking at this boring blank screen so far, and I want to go through an example of an annuity. And we'll define annuity first just as a series of regular payments. So that might be a payment to yourself in the form of a savings account, or it might be a payment to a bank to pay down a loan, for example. So a series of regular payments, and the kind of annuity that we'll be talking about is called an ordinary annuity, in which interest is paid at the time that a payment is made. So let's look at this example. Your book has an example too in section 6.3. You can look at that, but I'm going to recommend you go through this first and then maybe go back and read that example. So let's start out with this example. Suppose that rather than investing a lump sum up front, as in the previous examples, we will invest $100 per year, making 5 deposits at an interest rate of 10% compounded annually. That interest rate's pretty high. You probably wouldn't find that in reality these days, but it makes the example simpler, and so we'll use 10%. First thing to note is that this will be a 4-year investment. Now notice you're making 5 deposits, but here's how this goes. You make the first deposit of $100. The bank's not going to pay you interest on that at the moment that you deposit it. You have to leave it in there a year before you earn interest on that amount. Notice that interest is compounded annually. So you make this first $100 payment. It stays in the bank for a year, and then you get interest paid on it at the time during which you make your second payment. That second payment will sit in the bank for a year before it earns interest, and so on and so on. So that's why we're talking about a 4-year investment here. We make a payment up front, payment number 1. Second payment's made at the end of the first year. The third payment's made at the end of the second year. The fourth payment's made at the end of the third year, and the fifth payment's made at the end of the fourth year. So that's what we're looking at. All right, so let's look at this first payment. We'll break down all 5 payments and look at the performance of each one individually, and then at the end we'll add them all together. So first payment, A sub 1, the amount of the first payment, as soon as we put it in the bank, it has not had time to earn any interest. Notice that this formula that we're using here, we're back to the A equals P times the quantity 1 plus R over N to the NT that we use for lump sum investments, because we'll treat each individual payment of this annuity as a lump sum investment. So here's our formula. A equals P. P is just the amount of the payment that we're entering, so $100 times the quantity 1 plus R over N. R is 10%, N is 1 year. That's the frequency of compounding. And then to the NT, well, we're making 4 payments altogether, as we just discussed up here. This will be not 4 payments. We're making the payments over 4 years. So the first payment will be in there for a total of 4 years to earn interest. So we're raising it to the 4th power. I'm going to write that a little differently over here to the right. I'll just write it as being to the 5 minus 1 power. And the reason for that is to help you to be able to see the pattern that's happening here. Second payment, A sub 2, it will start out the value of $100. We've got 1 plus, again, our formula for compound interest, A times P times the quantity 1 plus R over N to the NT, 1 plus R over N. Well, this one will only be earning interest for 3 years, because this payment is made at the end of the first year of the 4-year investment. It's made at the time that interest is being paid for the first time on this payment number 1. So this one only earns interest for 3 years. Interest gets compounded 3 times. The next payment, payment number 3, only earns interest for 2 years. Payment number 4 only earns interest for 1 year. And the last payment earns no interest. It's made at the very end of the term of the annuity, the 4-year term. It earns no interest. So we've got 100 times the quantity, 1 plus 0.1 to the 0 power, which I've rewritten as to the 5 minus 5 power. If you're confused by any of these payment amounts, you can pause the video, go back and take a look at it again, play it again till it makes sense to you. Obviously, if you have questions, you can ask those through email or through Edmodo. I prefer that you ask them on Edmodo in case other people have the same question. Then I can just answer it one time instead of over and over again individually. So now we're going to look at how to develop the formula for the total value of this annuity, the sum of the values of all of the payments. And let's go here. So we're going to factor out a 100 because notice that each of these payments has a common factor of 100. Here, whoops, I didn't mean to do that. Here, 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 each one has 100. So we'll factor out 100, and then we'll add together all of these 5 payment amounts. So the first one, we'll start down at the bottom right here, and this is 100 times 1.1 to the 0, which is just 1. So when we factor 100 out of that, we're just left with a 1 here. This second term refers to a sub 4, so this one right here, we factor out a 100. We've got 100 times 1.1 to the first power, so here we go, 1 plus 0.1. This term refers to a sub 3. Factor out 100, you've got 1.1 to the second power, here it is. This term refers to a sub 2. Factor out 100, you've got 1.1 to the third power, there it is. This term refers to a sub 1. Factor out 100, you've got 1.1 to the fourth power, and here it is. And I didn't mean to do that. Excuse me. All right, here we go. We're going to generalize this. I'll back up just a second and point out to you up here that I don't like that the book does this, but they change variables on us. So whereas we were using R and N before, we're changing the meaning of things now. So our interest rate, the R over N that we were using for the compound interest formula, that now becomes I, lowercase I, not to be confused with the imaginary number I, it's different. And N is just the total number of payments to the annuity. So come down, convert these numbers to variables, and here the 0.1 is just the periodic interest rate I, so I'll substitute wherever there's a 0.1 up here, I'll substitute an I. Remember that N was the total number of payments, that was 5, so we express this 4 as N minus 1. And we'll just pull down these exponents here. That was a 1, 2, and so on up to N minus 1. We'd like to be able to find the total amount of the annuity. And we'll actually develop a formula for that. Here's how we'll do it. Whoops, I went a little too far. We'll multiply both sides of this equation. Let me circle that. Let me just circle the beginning. That's a little easier. Multiply both sides of this equation by the term 1 plus I. When we do that, we get what you see in this next equation here. In green, multiply both sides of this equation by 1 plus I. Pull this down. And then we're going to take the green equation minus the red equation. We get terms that cancel out in the middle. Notice I've got a 1 plus I here and here. Those are gone. 1 plus I squared here and here. Those are gone. All that's left when we take the green equation minus the red equation is what you see here. This equation. Divide both sides of that equation. We'll simplify the left and then divide both sides of the equation by I, and we get the formula that you see in section 6.3 of your textbook for the accumulated value of an annuity.